Okay, good morning and welcome to the Linley Fall Processor Conference. I'm Linley Gwennap and I'll be starting off today with our keynote presentation. So today I'll be talking about application-specific accelerators extending Moore's Law. In case you don't know me, I am the founder and principal analyst at the Linley Group, also editor-in-chief at Microprocessor Report, where I've written a lot of articles about AI processors and other processors, and including our guide to processors for deep learning. So today I'll be starting off with some information on application-specific accelerators, and then diving into AI acceleration, which is a key aspect of this trend, and then talking about specific markets, including the data center and the edge. So as most people know, Moore's Law is winding down. It's not necessarily dead in the sense that TSMC and other foundries are continuing to shrink the size of transistors. The first 5-nanometer processors are now in production, including Apple's A14 processor and the new iPhones. And TSMC does expect to continue progress with 3-nanometer production coming in a couple of years. But the problem is that we're just not seeing very much benefit from these new transistor nodes. Even though the transistors are getting smaller, the metal traces are also getting smaller, and that causes increased resistance, which slows down the signals and also tends to drive up the power. So even though the transistors are getting smaller, the metal traces are offsetting those gains. We're also seeing, in order to create these smaller transistors, we need more use of EUV, which is a very expensive technology for fabrication. We're seeing other complexities in the fabrication process, and that's causing the cost of the transistors to really not go down very much at all. So we're not seeing gains in cost either, and so this is just causing Moore's Law to slow down and even probably come to a stop at some point in the foreseeable future. So what this means is that we're just not getting very much performance gain from the smaller transistors. So as chip designers have to look at other ways to improve performance. And that's why we're seeing this trend toward application-specific architectures. By designing and optimizing the instruction set as well as the microarchitecture, we can accelerate inner loops by 10x or more to achieve much higher performance than a general purpose architecture. One method that we're seeing to improve performance is vector units, SIMD units, which allow a single instruction to perform many calculations in parallel, which can really reduce the overhead of loading and executing instructions. Another approach is to actually optimize and create customized data paths that are able to reduce the data movement in the chip, and that saves power. And really at a whole chip level, looking at how to combine the right amount of compute units, the right memory resources to create the best performance for a particular application while minimizing die area and power. So of course we saw this trend initially with things like graphics units, GPUs, DSPs, network processors. These were specific architectures optimized for these workloads. Now we're seeing things like AI accelerators using custom architectures, data processor units we'll be talking about at the conference, and storage processors that are all optimized for these specific applications. Now, looking in at the AI processors for a moment, we can see how that they are different from processors, general purpose processors. Even though we see these vector units in general purpose processors as well as GPUs and DSPs. They just don't go as far as they could in order to improve the performance. As the diagram here shows, the operands have to keep going in and out of the register file, and that causes a bottleneck. So what we're seeing, one approach we're seeing in AI accelerators is the use of systolic arrays. So as you can see from the lower diagram, in this case, the data moves directly from one function unit to the next without going through the register file. And this reduces power and allows more function units to be packed into the chip and accelerates the AI performance. Other things that we see in AI accelerators include specific hardware for common AI functions such as normalization and pooling. We also see AI accelerators typically using SRAM rather than cache to avoid the overhead of moving data back and forth between the different levels of cache. So there are all these different techniques that can be used to optimize the AI accelerator specifically for this emerging workload. Data processing units targeting more kinds of networking operations. So we see a trend toward moving networking functions from the host CPU into what's called a smart NIC, or a network interface card that has the capability to execute software-defined networking functions. This is more flexible than hard coding all of the protocols and operations, and allows these smart NICs to quickly be able to implement new features. So we see things like virtual routers, elastic storage, firewalls use this kind of technique to keep up with constantly changing networking operations. Because we're doing now these more complex functions on the smart NIC, it makes sense to optimize the design of that chip to better perform these functions. So we see custom architectures called DPUs being implemented to accelerate packet processing, to implement autonomous switching and routing, for example. Special protocols or emerging protocols, such as RDMA and IPsec, can be implemented in this way, as well as other common networking functions. So using these programmable engines, we can create software-defined functions combining bits and pieces of these operations in new ways, and optimize the performance on these networking functions. So we'll see more information on these DPUs in our session next week. In-memory compute is another emerging approach that's being used to optimize performance for certain workloads. As you can see in the diagram, in a standard system, you have a very wide memory, but then the compute unit only needs perhaps one word or one double word, which is extracted from all of the data that's loaded from that memory array. So if you have a problem that really requires a lot of parallel computation, you can break this bottleneck by having multiple compute units that all pull data from the array in parallel, and now you have utilized all of the data and eliminated a lot of the wasted overhead of throwing away the data in the mucks. So a lot of the power that's being dissipated in these chips today is actually in taking the memory and getting the data into the compute unit rather than the computation itself. So by breaking this bottleneck, we can really optimize and reduce the power that's required to move the data and then get more compute for a given amount of power. So we'll be hearing about several different ways to do in-memory computing next week on Thursday, and it should be a great introduction to this emerging technique. So now I want to switch gears and really dive into the AI accelerators in particular, since we'll be spending a lot of time over the next couple of weeks of this conference talking about AI and AI acceleration. One of the trends that we're seeing in the AI space is the model size. The models just keep getting bigger and bigger. We're seeing incredibly rapid growth. The latest model that's getting headlines is called GPT-3 with 175 billion parameters. And I drew a line here from the BERT model, which came out a couple years ago, up to GPT-3, and the slope is now 20x per year in the number of parameters. So incredibly rapid growth in order to deal with these very complex natural language problems, like understanding sentences and articles and being able to translate from one language to another. These problems require a tremendous amount of computation and a tremendous number of parameters in the model. On the other hand, if we look at the more traditional and established vision processing, image processing models, the growth has been a lot slower, maybe 2x per year, tracking from ResNet through Inception, through SENet and YOLO. These more modern models, and even just the past year or so, haven't seen much improvement there. So I think what we're seeing in image processing is that the models are getting to be very accurate, perhaps as accurate as they're going to get, and so there's not as much growth going on there. But if you're designing a chip to do the natural language processing, then you really need to be prepared to handle these very large models. Another trade-off we're seeing in AI accelerators is the number of cores and the size of the cores. So there's been a trend in computer architecture for a while. You can have big cores that deliver a lot of performance but are very complex, or you can break the problem down into multiple little cores, which you can more easily replicate across the chip. And both of these are valid choices. Both of them can deliver strong performance, and we're seeing a lot of different choices being made by different companies, as you can see on the chart here. We see anywhere from just one or two or a few cores from companies like Grok, Google's TPU, and then you can scale up to very large number of cores from companies like GraphCore and Cerebras, and even NVIDIA is sort of in the middle with over 100 cores on their latest chip. So the bigger cores I think simplify the software development, because you don't have to worry about parallelizing the task across so many different compute units. But they are harder to design and to get that much performance out of a single core or small number of cores. But another advantage of the big cores is on the latency side, because each core can put a lot of performance behind a single iteration of the model. You can usually get the job done more quickly, and for those applications that need low latency, the big cores can be a better solution. For applications that run with large batch sizes, it may not matter so much. Another emerging technique we're seeing is the convolution architecture. And this is particularly for these CNNs, which stands for convolutional neural network. So of course, by taking the core function in a convolutional neural network and really optimizing the hardware to execute that, you can even further optimize the performance. So instead of doing a general MAC operation or a general matrix multiply, this is specifically optimized to do the kind of 1x1 and 3x3 convolutions that are common in most image processing networks, as well as some of the language processing networks. So this architecture is great, for specific kinds of networks, but it may not be good, for other kinds of networks that use different kinds of convolutions or use fewer convolutions. So we see some companies taking this path, but these chips then become more specialized for the type of network they can handle. Another trend, which is played out in other arenas and we're now seeing in AI, is this issue of specialization. If you make your chip very specialized, such as using these convolution units, you can achieve the greatest possible acceleration for the function that you're specializing in. In this case, if you implement convolutions, you're very good at convolutional neural networks, but it may not work well for different kernel sizes that you're not optimized for. It may not work as well for other types of neural networks that don't use as many convolutions. So, a less optimized architecture, systolic array that just focuses on general matrix multiplication, could be more broadly used for AI. We also see, the smaller core architecture can be more flexible because you can break the problem up more granularly instead of having a single, large core that you have to fill. Obviously, CPUs are the most flexible. They're kind of general purpose by definition, but they also, are the least specialized and therefore tend to have lower performance on these types of algorithms. So there's a continuum here, and it's finding the right place in that continuum to find the right combination of flexibility versus performance to meet your customer needs. We've heard a lot about sparse computing lately, particularly in NVIDIA's most recent GPU. They've implemented something they call structured sparsity. So I wanted to take a minute to explain that. In general, sparse computing is about the fact that a lot of these matrices that you're multiplying, have a lot of zero values. And obviously, when you multiply something by zero, you get zero. And so, it's kind of wasting power to do that multiplication. And so the simple thing is to just disable a MAC unit when you determine that there's a zero operand. That saves a little bit of power, but you still don't get a MAC operation that cycle. So what NVIDIA's done is they pre-process the weights and take the ones, any weights that are zero, they can just X out, as in the diagram here, but also any weights that are close to zero also get X'd out. And the algorithm, it works in such a way that 2 out of every 4 weights are taken out of the original matrix. So so you may get some values that are actually not close to zero, but you always have to take out 2 out of every 4. So now you've achieved a 2-to-1 compression, and then the yellow bits show which weights have been removed. So when you actually perform the MAC operation, now you apply the same mask to the activations, mask out the ones that would normally go with the weights that are already zeroed out. You only do the multiplication for the weights that are left, and now you have doubled your throughput at the cost of removing half of the weights. So this does reduce the end accuracy a little bit because you have removed some non-zero weights, but according to NVIDIA, for most models, that accuracy reduction is pretty minor. You've doubled your throughput, and this is, of course, optional, so that if it doesn't work for a particular model, you don't have to use it. We expect that this type of approach, which is fairly well automated here in NVIDIA's tool set, will become more popular in other vendors as well. Obviously, there's different ways to spin this, whether it's 50% of the weights, 25% of the weights, 100%, well, obviously not 100, but a larger percentage. You could do things differently here, and I think we'll see a lot of innovation in this area of sparse computing to try to figure out what the best way to handle it is. But there's no doubt that that there's opportunities here for big performance improvements. Binary neural networks is another topic that people have been investigating. This is actually reducing the size of the weights instead of reducing the number of the weights. And of course, 1 bit is pretty much the minimum size you can use for a weight. So this is kind of as far as you can go. So of course, this reduces storage, it reduces power, reduces the amount of computation you need, but it does reduce the model accuracy as well. If you just kind of do this in a straightforward way, you can see pretty significant decreases in model accuracy. If you are a little bit clever about it, scaling and perhaps retraining the network, you can get the accuracy reduction down to a few percent. And then you can turn around and use some of the savings to perhaps use a more complicated network and get that accuracy back. So there's a lot of work being done in this area. Several vendors are implementing it as an option in their hardware so that you can try this out. It's not been widely deployed yet, but it does show some promise, particularly for specific types of models. Spiking neural networks is another approach, and we'll be hearing about that as well. This is an idea to which is really different from the typical deep neural networks that we're using. And you're really just looking for these binary activations to see whether you need to do something or not. If there's no activation, then there's no power being consumed. So this shows some promise in being able to reduce the size of networks, to reduce the power of networks. And again, there's several companies working on this. We'll be hearing from some of these companies over the course of the conference, and so we'll hear more details about how these neuromorphic computers work. Okay, so I want to talk about shift gears now and focus on what's going on in the data center. So as I mentioned, NVIDIA recently introduced their Ampere architecture. NVIDIA has been the leader in AI for the past few years. The Volta product that has been out on the market has been the best-selling processor for AI training. And then the Turing product that they introduced a couple years ago has been gaining ground for AI inference as well. So we're seeing that product displace Intel Xeon CPUs for a lot of the inference work. So this has caused a big boom in the AI market overall, in NVIDIA's revenue in particular, up 80% this year. So tremendous growth in AI over the last several months alone. And then this new Ampere product, offers strong improvements over the previous generation. 2.5 times performance on both integer and floating point. A lot more memory on the chip. So so NVIDIA has really raised the bar for everybody else in the data center AI market. Because of this, we're seeing some of the challengers struggling now. Even though Cerebras has brought out this huge product with 400,000 cores, but they haven't disclosed any benchmarks that show them exceeding the performance of Ampere. Graphcore also has a training chip that's in production. Even though they do a little bit better than the old V100, not really coming close to the new Ampere. with any of their release benchmarks. Intel acquired Habana for their training accelerator, but the production of the chip has been delayed. So we're not seeing any new benchmark results, from Intel on that chip. Huawei is also kind of in the same V100 class. So with the new bar that NVIDIA has set, they're looking pretty good on the training side. On the inference side, what we've seen is a drive toward greater power efficiency. This is kind of a weakness that the NVIDIA architecture has, that we need more power with those chips. So we've seen Qualcomm report the top Resonant 50 score, even outperforming the NVIDIA chip, but while using much less power. TensTorrent is a startup that's also offering a very strong performance at this lower power envelope. 75 watts versus 400 watts for the NVIDIA Ampere chip. Grok is offering similar performance to the A100 and very good latency. So that's a strength for Grok. Intel is kind of with their Habana chip kind of fallen behind. So we're waiting to see what Intel has in store for the next generation. Sambanova is another startup, but hasn't really brought out any details yet. So a lot of competition on the inference side, and and some benefits in terms of the power efficiency over NVIDIA. And we're also seeing a lot of the cloud vendors developing their own AI accelerators. Alibaba has really an impressive device called Hangguan that has the industry-leading ResNet score, and for a single chip by far. And they're deploying that in their cloud service to their customers. Google has, of course, been developing TPUs for a long time, and they're able to match NVIDIA's performance with the TPU V4, which has just come out. Amazon, Baidu have also developed their own chips, and starting to deploy those in the cloud as well. So these potentially take some sockets away from the merchant suppliers when the biggest customers are developing their own chips. Software has been a real struggle for a lot of these companies. NVIDIA has spent years investing in its CUDA infrastructure, so for other companies that are trying to compete, they have to duplicate a lot of that software stack. It's not just the compiler. Drivers have to plug into the frameworks that people are using to develop these models, and then other services that sit on top of those. And so what we're seeing is that although a lot of these companies can offer performance similar to NVIDIA's, they don't have the software, and in some cases, the customers try to run their models on this new software stack, and the models don't compile, they don't work, or they aren't optimized, so that you don't get the performance that you would expect. So it's easy to get Resonant 50 running, but trying to deliver a software stack that supports a lot of your customers' models, that's proven to be harder and taking longer for a lot of these competitors to deliver. So then moving on to the edge. So the edge means a lot of different things to different people. So let me start with the network edge. What we see in the service provider networks is more move to pushing the compute closer to the end user. So we see regional data centers. We see even these metro points of presence that are very small data centers that are located close to the customer, and this reduces latency. particularly for video and voice services that are sensitive, to latency. So, and we're even seeing some network service providers moving intelligence to the very edge of the network. For example, in cell towers that directly connect to the client device. So this requires then having not just CPUs, but potentially AI accelerators, network accelerators, DPUs, located in these small data centers and even at the edge of the network. So that is causing chip designers to start to focus on these environments. You need lower power, better thermal tolerance in order to work at the network edge. Cars are another potential aspect of the edge. These are basically client devices on wheels, and so we're seeing a drive, so to speak, to bring AI into the automotive market. The main application today is in ADAS. ADAS systems like automatic emergency braking or lane keeping assistance are starting to appear in most new vehicles. About 40% of all new vehicles sold in the world today include these kind of advanced automotive features, and the EU in particular is going to require emergency braking in all new vehicles by 2022. We expect the United States and other leading economies to follow. So that's going to continue to increase the use of AI in automotive. Of course, the end goal here is to achieve a fully self-driving vehicle, autonomous vehicle. This is obviously going to require more AI performance, more cost, hundreds of TOPS being required to achieve level 4 autonomy in these vehicles. So this adds a lot of cost. The sensors that are required add a lot of cost. So the problem is potentially solvable, but it is going to add a lot of cost to these vehicles, and probably not something we're going to see in mainstream consumer vehicles anytime soon. Another major challenge to autonomous vehicles is functional safety. If the car is driving itself and the CPU or whatever component fails, you don't want the car to have an accident or cause a problem. So it has to continue operating safely. And so there's some different approaches to functional safety that designers are contemplating. We'll be talking about those on Thursday this week. And so we'll dive into that topic in more detail. There's still making good progress in the road to autonomy, mainly in robo-taxis, not in consumer vehicles, as I said, but in more of a commercial, taxi service where you're getting rid of the cost of the driver and replacing them with the autonomous system. Even today, Tesla has said that they're going to be releasing a beta version of their full self-driving mode to their owners as an over-the-air update. So that's good progress. They've been promising that for some time. GM has deployed Super Cruise, which is a level 3, and driven. Their customers have driven millions of miles on that. We've seen Waymo remove safety drivers from its robo-taxis in their Phoenix service. GM has announced that they now will remove the safety drivers from their Cruise autonomous taxis later this year, in just a few months. And GM is committed to actually bringing this autonomous vehicle into production by 2022. So we do expect to see more robotaxis, in testing over the next year, 2022, commercial deployment of these robotaxis. And, ultimately within a few years, these kinds of features will start showing up in high-end consumer vehicles, not mainstream consumer vehicles. So we do expect to see, continued progress in this area. We also see the AI accelerators moving into client devices, and there's a lot of good reasons for that. Even though today most of the neural network applications execute in the cloud, moving some of that function to the client, reduces load on these cloud servers, reduces costs in the cloud data center, but it also benefits the user as well, reducing latency, improving reliability so that the service works even when the cloud is down or the network connection is down. And improving privacy as well by not exposing all of your data to the cloud service. So we see a lot of good reasons for this trend, and it's starting to take off. We see a lot of smartphones today, particularly all of the premium smartphones have some kind of AI accelerator built in. And we're starting to see this in other devices. For example, the latest Amazon Echo devices include a chip that has a hardware accelerator, and this allows them to process some of the Alexa voice commands in the device without going up to the cloud. It also helps do tricks like with the this Echo Show device in the picture here. If you stand in front of it and move around, the device will actually turn the screen to track you so that you can continue seeing the screen wherever you are, and so that the camera continues to track you as well. So there's some interesting tricks that you can use, that you can do with AI at the edge, and I'm sure that we'll continue seeing a lot of innovation there once these capabilities become more widespread. And then, more traditional embedded applications. We're starting to see companies jumping into this area, creating AI capabilities for these applications. These applications are easier to get into than the data center. Obviously, the performance targets are lower, and the number of networks that you have to run is generally pretty small. So that makes it a little easier, and we've seen a tremendous number of startups jumping into the market. I've listed several here, and this is just like a subset of everybody that we're trying to track right now. So we hear from some of these companies later this week, and some of them next week as well. Tremendous attention and innovation going on here in these embedded processors, and not just startups, but established companies as well. We're seeing leading microcontroller vendors like NXP and Maximum offering AI-enabled microcontrollers. We're seeing other established companies integrating AI into their existing products as well. So AI is moving from being a separate accelerator to really being a standard feature in a lot of these embedded processors. One way to put AI onto these very small devices is to use the microcontroller itself to execute the models. Even a small Cortex M class CPU can implement basic kind of vision functions, using a camera to determine if anybody's in the room, and then maybe you can turn off the lights or something if no one's in the room. So things like that can be useful and can be done with pretty simple hardware. If you want to do something a little more complicated, ARM offers something called the Helium SIMD functions. which run on Cortex M55. So you can get a big boost in AI performance just by using a more complicated microcontroller. And then, several companies are providing the software tools, of course, which are very important, to supporting this. We'll be hearing from Google next week at the keynote on Tuesday next to talk about this TensorFlow Lite for microcontrollers and this whole trend toward tiny ML. So hopefully you'll be able to come back for that. But if you want more performance in a small chip, I mean the microcontroller CPU itself is not going to be enough. So we're seeing these tiny AI engines that can deliver strong performance, billions of operations per second, while still maintaining very low power and cost. So these can go into small IoT devices and deliver some pretty strong AI capabilities on a small budget. So we'll be hearing from BrainChip later today and other companies talking about this kind of trend. And in order to assist these chip vendors, we're seeing more IP vendors delivering these tiny AI engines. ARM offers their Ethos accelerators for microcontrollers. We'll be hearing from Imagination and Think Silicon today to talk about their IP solutions. Cadence is presenting next week. So there's a lot of licensable IP available, for companies that are designing these low cost embedded processors. So just going to wrap up here. I don't have time to walk through the whole program for the conference. This is our biggest conference that we've ever had in terms of the number of presentations, the number of sessions. We've had to spread it out over 6 days to bring you all of the presentations through this virtual format. We're having several product announcements and disclosures at the event, so you'll hear a lot of things for the first time as you tune into these presentations. So I hope that you can attend as much of the event as possible and hear from a lot of these very interesting speakers. We also have breakout sessions at the end of each day. This is a good opportunity to spend more time with the particular speakers that you're interested in. We will have Q&A briefly after each presentation, but we can't take all of the questions. So the breakout sessions are a great opportunity to participate. And then new for this event, we've added the opportunity to have brief one-on-one meetings with the speakers. You have to sign up for those in advance. But if you're interested in having a detailed one-on-one meeting rather than the breakout session, you can go online, request that meeting, and have an opportunity to speak directly to the sponsor, to the speaker, about their presentation. So we're doing our best in these difficult times to give you as much opportunity to interact directly with the speakers, and hopefully you'll be able to take advantage of that. So in conclusion, then, we talked about Moore's law winding down, and that we need new architectures to improve performance, since the transistors just aren't going to do that for us. We're seeing a lot of competition in the data center, but NVIDIA still is maintaining a strong lead in performance, and so that's giving them an edge. Another advantage for NVIDIA is on the software side. It's difficult for a lot of these competitors to build up a software stack that competes with NVIDIA's. So I think that work is kind of ongoing. certainly we expect that to get better over time. On the embedded side, tremendous number of companies jumping into this market, a lot of great solutions out there, a lot of diverse solutions, and certainly the volumes are starting to take off, and we'll be hearing more from Google next week on this tiny ML trend, but we see that as another big opportunity to move AI out into even the smallest devices. So with that, I have time to take a few questions. Let me go back to the chat. If you want to ask a question, please submit using the Q&A button on the bottom of your screen. I see some people have already mastered that. What trends in compilers to support vector and SIMD extensions? We've seen some good work on general compilers to support vector extensions. What we're seeing now is more specific work that's focused on some of the AI specific applications. So some of the companies that are focusing on AI, obviously ARM, NVIDIA are focusing on this, so the compilers are supporting some of the new AI algorithms. What are your thoughts on startups that try different approaches for AI acceleration? Analog computing, optical computing. Naturally, I think, the first wave of startups we saw were focused on, more, say traditional approaches, digital approaches. And, we've seen some good results there. I do think that analog or optical could offer another big wave of performance. But so far we haven't seen actual products in production to demonstrate that. So we'll be hearing more about analog computing in the in-memory session next week, and optical it's a little bit early, but it is an area where we should be seeing some results soon, and then we'll really see if that technology is ready for prime time. Question about what is the most promising avenue for broad industry software development that would be an alternative to CUDA? Yeah, so that's a good question. I mean, so there are some open efforts that are going on, but they're not getting a huge amount of traction. So it's really been up to most of the companies to develop their own alternative, and that's why it's been taking so long. Companies like Intel and Qualcomm have good software stacks. They're obviously are heavily invested in software on a number of fronts, and have the resources to do that. We're seeing some progress from some of the the well-funded startups are making some good progress with their software stacks. But yeah, it's just going to take time, and and I think there's probably going to be some consolidation at some point to help some of these companies increase their software investment. Unfortunately, that's all the time I have for questions, but I will be taking more questions during our breakout session at 12 o'clock noon Pacific time. So please, if you have more questions, stop by the breakout session, and otherwise, hopefully you can enjoy the rest of the show.